In the stillness of night, when the sky above unfolds in its quiet splendor, it is easy to mistake the universe for a gentle sea of light. Stars appear as delicate pinpricks, scattered like diamonds on velvet, and the great river of the Milky Way drifts as though painted by a divine hand. Yet beyond that illusion of serenity lies a reality far less forgiving. Space is not a silent sanctuary. It is a battlefield of unimaginable power, a realm where creation and annihilation coexist in violent balance. The Earth is a fragile cradle, wrapped in the thinnest veil of atmosphere and magnetism, protecting life from the fury that reigns outside. But just beyond that protective shell begins a wilderness so hostile it defies human comprehension. Radiation scours the void. Temperatures plunge toward absolute zero, only to be interrupted by furnaces hotter than 1 billion suns. Invisible particles, born in cataclysms, light years away, pierce through worlds as though matter were nothing at all. There are places where entire stars collapse under their own weight, becoming black holes that swallow not only matter, but time itself. Others spin as pulsars, lighthouses of death, their beams of radiation sweeping space like cosmic scythes. Far more terrifying are gamma-ray bursts, eruptions, so violent they could sterilize a galaxy in moments, outshining all the stars in the cosmos combined. These are not distant curiosities. They are forces that sculpt galaxies, dictate the fates of worlds, and, if aimed in our direction, could extinguish life in an instant. The universe is not merely vast, it is dangerous. And as humanity dreams of venturing beyond its birthplace, a question lingers like a shadow. What does it mean to step into a cosmos where survival hangs by the thinnest of threads, where wonder and death are bound together in the same eternal dance? Long before the first instruments reached toward the stars, long before equations could measure their light, humanity gazed upward in awe. To the earliest eyes, the heavens appeared as an untouched canvas, eternal and serene, free from the imperfections of Earth. The night sky was interpreted not as a place of violence, but as the dwelling ground of gods. Ancient cultures wrapped its lights in myths of power and immortality. The Greeks imagined Orion hunting forever among the constellations. The Egyptians traced the soul of Osiris in the bright star Sirius, marking the floods of the Nile. To the Polynesian navigators, the stars were guides, whispering safe passage across a dark ocean. To the Maya, they were clocks of destiny, recording the cycles of time itself. Yet within these myths lay an unconscious recognition of the power above. The gods of the heavens were rarely gentle. They hurled thunderbolts, commanded storms, and presided over death. Lightning from the sky, the sun's searing strength, and meteors that streaked with fire, all were reminders that the heavens could wound as much as they could inspire. Humanity's first cosmic stories were not wrong. In essence, they sensed, without knowing, that above Earth's fragile shelter resided forces capable of ending worlds. For centuries, however, this vision remained framed in superstition. The stars were eternal pinpricks, fixed in a crystalline sphere, serene and unchanging. It was the Earth that was thought to decay, not the heavens. Then came the revolutions of the Renaissance. Nicolaus Copernicus dared to suggest that Earth was not the center, but merely one wanderer among many. Galileo Galilei raised his telescope to the night sky and shattered illusions. What he saw was not divine perfection, but roughness, chaos, and storms. The moon was pitted with scars. Jupiter was orbited by its own tiny moons. miniature worlds dancing around a giant. Saturn bore rings so delicate yet alien they defied comprehension. And the sun, the eternal giver of life, revealed dark blemishes, sunspots, vortices of magnetism larger than Earth itself, boiling with unseen violence. With each discovery, the myth of heavenly serenity collapsed. The telescope revealed not gods but physics, not perfection but turbulence. Comets, once feared as omens of death, now became icy wanderers traced by Newtonian laws. Supernova, observed in the 16th and 17th centuries, showed that stars could die, collapsing into explosions brighter than galaxies. The heavens, it seemed, were not eternal at all. They were changing, dynamic, and sometimes catastrophically violent. As the Enlightenment spread, so too did this unsettling recognition. The universe was not built for human comfort. Beyond the thin veil of Earth's atmosphere stretched an abyss, with no air to breathe, no water to drink, no warmth to sustain life. The vacuum itself was hostile, a suffocating void that stripped life away in seconds. The sun, while nurturing, hurled out storms of radiation capable of killing a man on the moon if unshielded. Lightning and auroras on Earth hinted at the charged fury of particles spiraling down magnetic fields from space. Bit by bit, the dream of the stars as tranquil guardians gave way to the truth of a hostile environment. And yet, even as telescopes revealed storms and explosions, the true scale of cosmic danger was still hidden. The instruments of the 17th and 18th centuries could not yet sense the invisible. They could not detect the silent hail of radiation constantly raining down from beyond the solar system. They could not measure the subatomic bullets called cosmic rays, each particle carrying the energy of a speeding car, slamming into Earth's atmosphere by the billions every second. For now, humanity still believed that the deadliness of space was limited, a matter of cold, of vacuum, of distance. The 19th century began to stretch those boundaries further. Spectroscopy revealed that stars were not simply lights, but furnaces, nuclear fires raging in equilibrium. They burned with power so intense that it bent the very fabric of matter. Astronomers began to understand that stars were not eternal. They lived and they died. They consumed themselves, and in that consumption was born both creation and destruction. The discovery of novas and supernovas provided unsettling confirmation. A star could, in a single instant, unleash more energy than all the light shining from the billions of stars in the Milky Way combined. It was a revelation that shook the human imagination. As telescopes grew sharper and instruments more refined, the 20th century brought humanity to the brink of a profound realization. Space was not merely hostile, it was lethally extreme. When Robert Millikan studied cosmic rays in the early 1900s, he revealed that Earth was bathed in invisible radiation from above, high-energy particles accelerated by events beyond imagination. Observatories captured light curves of distant supernova and noticed patterns hinting at collapsed remnants. Neutron stars and black holes, objects so dense that even the language of physics strained to describe them. Einstein's theory of relativity reframed space not as a passive backdrop but as an active fabric, bending, twisting, collapsing under immense masses. The heavens were no longer a celestial dome, but a dynamic stage of warping geometry, time itself dragged into chaos. And then, for the first time, humans themselves dared to leave Earth's cocoon. With the dawn of the space age in the mid-20th century, rockets carried fragile bodies into orbit. It was then that the lethal nature of space became undeniable. The vacuum, the radiation, the storms from the sun, all were encountered. Not in theory, but in practice. Satellites revealed belts of charged particles trapped around Earth, invisible rings of radiation that could kill an unprotected astronaut in hours. The Apollo missions skirted these belts, threading a narrow path of survival, never straying beyond the shelter of Earth's magnetic field for long. What had once been myths of divine punishment became scientific realities of cosmic hostility. Space, it turned out, was not indifferent to life, but actively opposed to it. It was an arena where survival required ingenuity, shielding, and constant vigilance. The dangers above were no longer distant ideas. They were measurable, quantifiable, and deadly by the late 20th century. With X-ray and gamma-ray observatories lofted into orbit, humanity began to see the universe in its true colors. Pulsars flashed with relentless precision, lighthouses of collapsed stars spinning faster than a kitchen blender, their beams of radiation lethal to anything in their path. Magnetars, with fields strong enough to rip electrons from atoms across vast distances, emerged as among the deadliest objects known. Gamma-ray bursts, discovered by satellites meant to police nuclear weapons, revealed themselves as cosmic detonations capable of erasing life across entire star systems in a heartbeat. The serene dome of the night sky was gone forever. In its place emerged a universe that was both terrifying and magnificent, a realm of extremes where beauty and death were inseparably entwined. Humanity had uncovered not only its origins among the stars, but also the lethal forces that lurked there, waiting, silent, patient. The realization marked a turning point. Space was no longer simply the backdrop for myths or the stage for navigation. It was an active, dynamic, and deadly landscape. And as the 20th century gave way to the 21st, the story of discovery shifted once more from awe to confrontation, from seeing to enduring, from the recognition of danger to the attempt to understand its deepest nature. The origins of our awareness had been laid. The universe was vast, and it was alive with forces that could unmake us in moments. Humanity now knew the truth. The stars were not only lights of hope, but harbingers of peril. Yet even with these revelations, the human imagination clung to the comfort of distance. The stars were violent, yes, but they were far away, their eruptions visible only as fading smears of light across the heavens. Supernova glowed in history's records, but none had seared itself close enough to Earth to reveal the immediacy of their threat. It was easy, in those centuries, to believe the violence belonged to another realm, detached from the safety of our own world. But the truth was already pressing upon us, written in the meteor craters carved into Earth's crust, in the silent scars left by ancient impacts. The heavens had struck before, and they would strike again. The myths of gods casting down fire were, in this light, not fictions, but echoes of remembered catastrophes. The Tunguska event of 1908, when a fragment of rock from the cosmos tore through Siberia's skies and flattened forests the size of entire nations, brought this truth into sharp relief, though not yet tied directly to the cosmic scale of supernova or gamma-ray bursts. It was a reminder that death from above was not hypothetical. It had happened, and it would happen again. Humanity's sense of fragility was beginning to sharpen. The 20th century made it impossible to ignore. Balloons lofted into the upper atmosphere carried instruments that ticked relentlessly as they counted invisible particles raining down from space. Cosmic rays were no longer mythic arrows from the gods, but high-energy messengers from beyond. Our galaxy, some accelerated by black holes, others by the shock waves of exploding stars. They struck the atmosphere like bullets, splitting atoms, creating showers of secondary particles that cascaded to the ground. The discovery was as unsettling as it was profound. Earth was not shielded from the universe. It was immersed in it, constantly bombarded by the byproducts of violence unfolding across light years of distance. For the scientists of the era, this knowledge carried a dual weight, a scientific wonder at the mechanisms of acceleration and an existential recognition of vulnerability. If particles with energies far beyond anything humans could create in laboratories were constantly arriving, what had forged them? What furnaces, what cataclysms could produce such violence? The search for answers led to the recognition of black holes and neutron stars not as abstractions, but as real astrophysical engines. The universe's most extreme phenomena were no longer theoretical curiosities buried in equations. They were the living, deadly architects of the cosmos, still shaping the universe we inhabit. The Copernican revolution had stripped Earth of its centrality, but the revelations of the 20th century stripped the heavens of their serenity. The recognition was devastating in its philosophical reach. For millennia, humanity had lifted its gaze to the stars in search of guidance, believing them to be eternal, flawless, perhaps even benevolent. Now it became clear that they were none of these things. Stars were born, they lived, and they died. Their deaths were not quiet, but violent beyond imagination. And from those deaths came consequences. Radiation fields stretching across galaxies, shock waves capable of sculpting new generations of stars, and beams of energy that, if aimed by chance, could sterilize entire worlds. This realization ushered in a new era of human thought. The universe was not designed for life's comfort. It was indifferent at best, hostile at worst. Life on Earth persisted only within a narrow, precarious balance, a fragile island shielded by magnetic fields, atmospheres, and distance. Beyond those protections lay a realm fundamentally opposed to survival. Every telescope, every balloon experiment, every satellite that pierced the veil confirmed this with greater clarity, and yet, with every revelation of danger came a paradoxical deepening of awe. For in this lethal environment, somehow, against impossible odds, life had taken root. The very forces that threatened annihilation were also the engines of creation. Supernova, while destructive, seeded space with the heavy elements necessary for planets, oceans, and living bodies. Cosmic rays, though deadly in excess, may have spurred the mutations that helped life evolve. The duality of the cosmos, its power to both create and destroy, lay exposed. Humanity was beginning to understand not just that space was deadly, but that its deadliness was inseparably bound to the existence of life itself. The journey from myth to science had revealed a universe more violent, more dangerous, and yet more extraordinary than the ancients had ever dared to imagine. From the first flickers of superstition to the hard truths of physics, humanity had finally begun to grasp the reality of its cosmic environment. The origins of this discovery were humbling. The night sky was not a sanctuary of gods, but a crucible of forces, a deadly theater where destruction reigned as much as beauty. And standing upon Earth's fragile surface, shielded by chance and circumstance, humanity began to look upward with a new kind of reverence, not for the benevolence of the heavens, but for the raw, unrelenting power they contained. At the dawn of the 20th century, the night sky seemed largely mapped, its major secrets already catalogued. Telescopes had revealed planets, moons, nebulae, and galaxies. Newton's laws described their motion. Maxwell's equations explained their light. To many, it seemed as though the universe had surrendered its mysteries, standing still and eternal in a framework of order. But nature had one final veil too. Lift, and it would be revealed not by sight, but by something far more elusive. An invisible rain falling ceaselessly upon the earth. When physicists placed electroscopes in shielded boxes at the beginning of the century, they expected stillness. But the instruments continued to discharge. Something unseen was striking them, something penetrating stone and lead. The answer came from balloons that drifted into the upper atmosphere, carrying instruments higher than ever before. As they rose, the mysterious effect grew stronger, not weaker. The discovery was astonishing. Earth was being bombarded by high-energy particles from beyond its boundaries. They called them cosmic rays. These rays were not like ordinary radiation. Some carried energies millions of times greater than anything produced on Earth. They arrived relentlessly, day and night, indifferent to seasons or geography. What could forge such weapons, capable of piercing the atmosphere and striking detectors? Hidden deep underground, the implication was unsettling. Somewhere in the universe, events of staggering violence were hurling particles into space with unimaginable force. The night sky, which seemed so tranquil, was in truth a battlefield of energies unseen. Albert Einstein's theory of relativity only deepened this vision. In 1915, his equations revealed that space was not a passive emptiness, but a flexible fabric that bent, curved, and collapsed under the weight of mass and energy. Gravity was no longer an invisible tether pulling planets into orbits. It was space-time itself being warped and twisted. A black hole, once considered little more than a mathematical curiosity, now emerged as a real possibility, a place where gravity became so extreme that even light could not escape. Suddenly, the heavens appeared alive with potential hazards, unseen distortions, hidden abysses where the familiar rules of time and matter broke apart. While Einstein unveiled a dynamic cosmos, astronomers uncovered its scars through radio telescopes, and later X-ray observatories. They began to trace the remnants of ancient explosions scattered across the Milky Way. Nebulous clouds of gas expanded outward like bruises on the galaxy's skin, the aftershocks of supernova. These were not gentle deaths of stars, but catastrophic detonations, the collapse of giants whose cores had failed under their own gravity. A single supernova could outshine its entire host galaxy for weeks, releasing more energy in a heartbeat than the sun would emit in 10 billion years. These remnants, still glowing centuries later, were proof that the sky was not peaceful but violent, marked by battles where stars destroyed themselves in spectacular fury. The shock was philosophical, as much as scientific. For centuries, the heavens had been treated as symbols of permanence. Stars were used to guide ships, to measure time, to anchor the rhythms of civilization. Now it became clear that those same stars lived precarious lives, burning furiously, before collapsing in violent death. Creation and destruction were woven into the same fabric, inseparable and necessary. If such violence was the engine of the cosmos, then stability, the very condition life depended on, was the exception, not the rule. Scientists wrestled with a paradox. The elements that built Earth and the bodies of all living things were forged in those very cataclysms: carbon, oxygen, iron. The building blocks of biology were born inside the hearts of massive stars and scattered by their explosions. The deadliest events in the universe were also its most creative. Life was both threatened by and indebted to violence. The cosmos was revealed as a crucible where death was not an end but a transformation, a cycle without mercy yet full of consequence. In the laboratories of Europe and America, as cloud chambers revealed streaks of unseen particles, the philosophical weight grew heavier. Each track was a reminder of forces beyond imagination, of distant explosions whose echoes arrived as messengers of destruction. The cosmic rays were relentless, and though Earth's atmosphere shielded us from their worst, their very existence hinted at the vast reservoirs of energy active in the universe. Astronomers began to look outward with a new caution, no longer assuming the heavens were benign. Every nebula might be a wound, every pulsar a reminder of a star's death throws by the mid-century. With radio astronomy advancing, pulsars were discovered, neutron stars no larger than a city but denser than anything imagined, spinning rapidly and beaming radiation into space like cosmic lighthouses. Each flash was the heartbeat of a collapsed star, the remnant of a supernova so intense that it had crushed matter into a state no earthly experiment could reproduce. For the first time, scientists could study the aftermath of stellar violence, not as speculation, but as observable reality. The reactions to these discoveries were not uniform. Some embraced the revelations with awe, marveling at the extremes nature could produce. Others were unsettled, even haunted, by the realization that Earth existed in a cosmos neither safe nor stable. The universe that birthed life was also riddled with traps and hazards, many invisible, all indifferent. To confront this truth was to confront a deeper question. If the universe was so violent, how had life arisen at all, and how long could it endure? In quiet observatories and bustling universities, debates raged not only about the mechanics of these deadly places, but about their meaning. Was life a fragile accident, sheltered by chance from the universe's hostility, or was violence itself necessary for life's emergence, the destructive events of the cosmos sowing the very seeds that made existence possible? The question was less about science than philosophy, reaching into the oldest traditions of human thought. The stars no longer offered reassurance. They demanded humility. As the 20th century advanced, the weight of these first discoveries pressed deeper. Cosmic rays, relativity, supernova remnants, all spoke with the same voice. The universe was not what it seemed. Behind its beauty lay lethality. Behind its light lay shadows of violence. The heavens were not only vast, but alive with energy, restless and unforgiving. Humanity had opened its eyes, and for the first time it understood. To venture outward would not be to sail upon calm waters, but to step into a storm. The story of cosmic rays unfolded with both wonder and unease. In 1912, Austrian physicist Victor Hess carried his instruments high into the sky aboard a hydrogen balloon, ascending nearly 5 kilometers above the Earth. What he found astonished him. Instead of diminishing with altitude as ordinary radiation from the ground should, the mysterious ionizing effect grew stronger. The higher he climbed, the more intense the invisible bombardment became. His daring experiment proved beyond doubt that radiation was arriving not from below, but from above, falling constantly upon the Earth from the cosmos itself. The discovery carried profound implications. If the heavens rained invisible energy, then every living thing had been, since its beginnings, immersed in a storm of particles born in distant catastrophes. Hess had revealed that the apparent tranquility of the sky was an illusion. Above the clouds, beyond the blue, lay a constant hail of violence. particles accelerated by events far beyond human comprehension. Robert Millikan later coined the term cosmic rays, describing them as messages from the birth of atoms, though even he struggled to accept the sheer magnitude of energy they carried. Some single particles, struck with the energy of a well-thrown baseball, concentrated into a point smaller than a proton. To conceive of an engine capable of producing such force stretched imagination and theory alike. The philosophical weight of these findings was immense. Humanity, which had long placed itself at the center of a calm universe, now stood exposed. In a restless storm, Earth was not isolated but vulnerable, struck constantly by emissaries of death from stars long dead, from black holes feeding in silence, from galaxies tearing themselves apart. It was a revelation that blurred the line between science and existential reflection. What kind of universe birthed life only to surround it with perpetual hazards? Was survival an act of chance, a fragile balance shielded by Earth's atmosphere? Or was it a testament to life's improbable resilience against impossible odds? As the decades progressed, new instruments revealed more. By mid-century, cloud chambers and later bubble chambers traced the delicate scars left by cosmic rays as they passed through. Physicists watched as these invisible messengers etched streaks of condensation in their detectors, as though the universe itself was writing in vapor. Each streak told a story of violence far away, a star's death throes, a galactic collision, a supermassive black hole devouring its prey. To look at these tracks was to glimpse a cosmos forever at war with itself. At the same time, Einstein's general relativity was rippling through physics, altering the very conception of what space was. If space-time could bend and collapse, then extreme objects, black holes, neutron stars, and warped gravitational fields were not just curiosities, but inevitable realities. Relativity predicted regions where time slowed, where matter fell into oblivion, where light itself could be trapped. The universe was not static, not gentle. It was a dynamic landscape, alive with distortions, governed by laws that permitted both creation and destruction on scales that dwarfed imagination. Supernova remnants added still more evidence to this vision. Observatories captured immense shells of gas and dust expanding outward from ancient detonations, ghostly remains of stars that had perished in violence. The Crab Nebula, still glowing with furious energy from an explosion recorded by Chinese astronomers in 1054, became an icon of this truth. The heavens could unleash devastation on scales that reshaped galaxies. Within its heart lay a pulsar, a neutron star rotating 30 times a second, sending out beams of radiation like the sweep of a cosmic scythe. Such discoveries forced scientists to reckon not just with the mechanics of death in the cosmos, but with its implications. For many, the recognition was both unsettling and strangely poetic. The same forces that destroyed stars also seeded new beginnings. The heavy elements scattered by supernova created the raw material for new worlds, for oceans, for blood and bone. Iron in the hemoglobin of human blood was born in stellar explosions. Calcium in bones was forged in the heart of stars. Even the gold adorning human civilizations came from violent collisions of neutron stars flung across the galaxy in waves of debris. Life was not separate from cosmic violence, but inseparable from it, a child of fire and fury. And yet, for every revelation of creation, there remained an undeniable sense of danger. The crab's pulsar would vaporize any world unlucky enough to drift into its beam. The cosmic rays striking Earth were the faintest whispers of storms raging across the galaxy. storms that could sterilize entire planets. The beauty of the night sky now carried a hidden menace. The heavens were alive with invisible hazards, indifferent to the survival of those who gazed upon them. Scientists began to grapple with the philosophical contradiction. How could the universe produce consciousness within such fragile vessels, yet surround it with such overwhelming hostility? Was life the rarest of accidents, nurtured by improbable shielding on one small planet? Or was it a natural outgrowth of the same cycles of destruction and rebirth? For some, the answer lay in humility. Humanity was not central, not protected, but precarious, a brief flicker in a cosmos of extremes. For others, it was cause for awe. That life had arisen at all within such conditions was itself a testament to the universe's capacity for balance. Amid violence, the early 20th century thus marked a turning point in human understanding. The first scientific reactions to the violent universe revealed a cosmos that was neither safe nor stable. Every discovery, cosmic rays, relativity, supernova remnants, drew the same conclusion. Space was not a silent sea, but a storm. The stars did not merely shine, they lived, they died, and in dying they shaped the very fabric of existence. To confront this truth was to confront the fragile position of humanity in the grand design. The universe was vast, magnificent, and deadly, and humanity, now aware of the danger, stood at the threshold of a new era, an era of reckoning, where wonder and fear would intertwine with every gaze into the night. By the middle of the 20th century, the ancient sky that had long been studied from mountain peaks and observatories was no longer distant. The space age had begun, and for the first time, humanity dared to send machines, and then lives into the very domain once thought unreachable. Rockets pierced the atmosphere, carrying with them fragile capsules of metal and glass into an environment where Earth's protective veil no longer held. What they found confirmed the suspicions born of Hess's balloon flights and Einstein's equations beyond the cradle. The universe was not calm. It was dangerous. The first satellites carried more than cameras. They carried Geiger counters and detectors, their purpose not only to measure the silence of orbit, but to listen for invisible threats. Almost immediately, they revealed that Earth was not drifting unprotected in the cosmic tide. Surrounding the planet were vast belts of trapped radiation, donut-shaped prisons of charged particles caught by the magnetic field. Discovered in 1958, the Van Allen belts became a revelation. Earth was not merely orbiting in a void, it was sailing beneath an invisible shield, a magnetic cocoon deflecting cosmic rays and solar storms. Without it, life would have been impossible. With it, the planet was spared the worst of the cosmic rain, though not always entirely. These belts, beautiful in theory, were deadly in practice. For astronauts traveling through them, exposure meant a hidden risk, an unseen hazard capable of inflicting lethal doses of radiation in hours. Engineers and mission planners learned that to cross them was to navigate a minefield of energy, where survival depended on trajectory, timing, and the fragile shielding of thin aluminum walls. The knowledge that humanity lived only because of a magnetic embrace reshaped the image of Earth, from a safe harbor to a precarious island in an ocean of threats. The danger became more personal during the Apollo missions. Between 1968 and 1972, astronauts left the protection of low Earth orbit and entered the true void. They carried with them not just dreams of exploration, but mortal risks. On the journey to the moon, the crew was exposed to radiation that would have been catastrophic had a solar storm erupted in those days. In August 1972, between the flights of Apollo 16 and Apollo 17, the Sun released a solar flare so powerful it could have killed an unshielded crew in transit. The astronauts were spared by chance, the timing of human ambition narrowly avoiding a fatal storm. It was a sobering reminder that space was not empty but alive, a place where survival itself could depend on the shifting moods of a distant star. At the same time, instruments turned outward, seeking to uncover the true nature of the violent heavens. The first X-ray telescopes, carried aloft by rockets and balloons, revealed skies unlike anything known to human eyes. Where once the night appeared serene, the universe in X-rays was a canvas of chaos. Collapsed stars screamed into the detectors. As pulsars rapidly rotating neutron stars, their beams of radiation sweeping across the cosmos like lighthouses of death. These objects, first discovered in 1967 by Jocelyn Bell Burnell, pulsed with terrifying precision, a cosmic heartbeat measured in milliseconds. They were the remnants of stellar explosions, objects so dense that a teaspoon of their matter weighed as much as a mountain, spinning with relentless energy. For the first time, humanity glimpsed stars not in their glory, but in their afterlives, stripped of light yet burning with invisible fury. The revelations did not stop there. During the height of the Cold War, satellites designed to detect nuclear detonations on Earth's surface picked up something unexpected. In the mid-1960s, the Vela satellites, meant to ensure compliance with nuclear treaties, recorded sudden, intense flashes of gamma rays, the most energetic form of light known. These bursts did not come from Earth, nor from the Sun. They came from deep space. At first, they were a mystery shrouded in secrecy, hidden by governments unsure of their origin. But as data accumulated, it became clear the sky itself was erupting. Somewhere across the cosmos, unknown cataclysms were unleashing torrents of energy capable of outshining entire galaxies in seconds. These gamma-ray bursts became one of the greatest enigmas of modern astronomy, a puzzle that would haunt scientists for decades. By the end of the 1960s, a new image of the universe had taken shape. The cosmos was not merely a tapestry of stars and gentle nebulae, but a battlefield of extremes. Earth orbited within a magnetic shield, but beyond it stretched dangers unimaginable. Pulsars that shredded matter, neutron stars born from collapse, solar storms that could fry electronics and lives, bursts of gamma radiation that arrived without warning, carrying energies impossible to reproduce on Earth. The catalogue of deadly places was beginning to form, one discovery at a time, each more unsettling than the last. And yet, woven through these discoveries was a paradox. The very forces that threatened also illuminated. Radiation belts revealed the power of Earth's magnetosphere. Pulsars unveiled the inner workings of stellar death. Gamma-ray bursts hinted at events far beyond ordinary comprehension. Every deadly place was also a clue, every threat a doorway to deeper understanding. To study danger was to confront the universe in its most honest form, indifferent, violent, and yet profoundly creative. By the close of the early investigations, the dream of exploration was forever altered. Space was not a blank slate awaiting human conquest. It was a living arena, fierce and unforgiving. The pioneers of the space age had pulled back the veil, and what they found was both magnificent and terrifying. Humanity now stood between wonder and fear, looking outward with a mixture of awe and caution, knowing that beyond the thin shell of Earth lay a cosmos of death as much as of beauty, a universe that would demand respect with every step forward. Discovery of the Van Allen belts had not come easily. When James Van Allen and his team first launched the Explorer 1 satellite in January 1958, their mission was not to map invisible armor, but to simply place instruments into orbit and begin listening to the cosmic environment. What they found startled them. Their Geiger counters registered radiation levels so intense that they sometimes saturated the detectors entirely, leaving blank readings where the signal was too overwhelming to process. At first, it seemed like a failure of technology, but as subsequent launches confirmed the data, the truth emerged. Earth was wrapped in vast rings of trapped charged particles, sculpted by the magnetic field into toroidal prisons extending tens of thousands of kilometers into space. These belts were both protector and threat, a shield keeping the most dangerous particles from reaching the ground, and yet also a hazard to any who dared to venture through. For astronauts, the belts represented a paradox of vulnerability. To cross them quickly was safe enough, but to linger was to court death. The energy within the inner belt was strong enough to strip cells, to fracture DNA, to poison the body. Invisibly, engineers charted safe paths through the weakest regions, calculating trajectories with a precision that left little room for error. The understanding of the belts was more than scientific curiosity. It was a survival strategy. Every journey to the moon had to thread this dangerous needle, relying on both mathematics and fortune. Humanity's leap into space was not a conquest of emptiness, but a negotiation with forces that could not be tamed. The Apollo missions revealed just how fragile that negotiation was. Between April and December of 1972, during the height of lunar exploration, the sun grew restless. On August 4th of that year, a massive solar storm erupted, releasing a flood of protons so intense that any astronauts en route to the moon at that moment would have received doses of radiation well beyond lethal limits. Shielding within the thin hull of the command module would have been insufficient. Their survival would have been measured in hours. By sheer luck of timing, the Apollo crews missed the storm. History would later reflect on this as a silent near catastrophe, a moment when humanity's greatest triumph might have been its first tragedy beyond Earth. It was a reminder that the cosmos is indifferent to ambition, and that every step outward was shadowed by invisible danger. While human explorers risked their lives, machines carried eyes sensitive to new forms of light. For centuries, astronomy had been bound to the narrow window of visible light, the same range of wavelengths the human eye had evolved to perceive. But the universe spoke in many voices: X-rays, gamma rays, radio waves, and to hear them required instruments above the suffocating blanket of atmosphere. Balloons first carried detectors into the upper sky, and later, rockets lifted them higher still. The results were staggering. In 1967, Jocelyn Bell Burnell, a graduate student at Cambridge, noticed something unusual in the miles of chart paper produced by a radio telescope she had helped to build. Amid the background noise, she found a signal repeating with extraordinary regularity, a pulse every 1.3 seconds, steady as a clock. At first it seemed so unnatural, so precise, that her team jokingly labeled it LGM1 for little green men. But it was no artifact of alien design. It was the heartbeat of a collapsed star, a neutron star spinning with unimaginable speed, its radiation sweeping across space like a cosmic beacon. The discovery of pulsars was a revelation. The deaths of stars did not always produce silence. Sometimes they produced monsters, dense spheres no larger than a city, spinning faster than a kitchen blender, hurling energy across the cosmos. These were not distant curiosities, but potential threats. Any planet caught in their beams would be scorched into lifeless centers. In the same years, the skies betrayed another secret. The Vela satellites, launched by the United States to monitor nuclear explosions on Earth, carried detectors for gamma radiation. But in 1967, they picked up flashes that did not fit the pattern of any weapon test. They came not from Earth, not from the sun, but from the distant heavens. Each flash lasted only seconds, but the energy released dwarfed anything humans could imagine. For years, the data remained classified, concealed beneath Cold War secrecy. Only in the 1970s did the truth emerge. The cosmos itself was detonating in events so violent that even supernova paled in comparison. Gamma bursts were unlike anything else known, brief yet blinding, their origins uncertain. Were they the collapse of massive stars into black holes? The collision of neutron stars spiraling together in a final embrace? Or something stranger? Still, the discovery shook astronomy at its core. Humanity had once believed the greatest dangers lay within reach: comets, asteroids, storms of the sun. But the Vela satellites revealed that the most terrifying threats came from across the universe, striking without warning, untraceable until they arrived. These events might occur billions of light years away, yet their light was powerful enough to reach Earth. Should one erupt in our galactic neighborhood, it could strip the ozone from Earth's atmosphere in seconds, bathing the planet in lethal radiation. The fact that life continued at all was once again a reminder of the thin margins by which it existed. By the close of the 1960s, the portrait of space had changed irrevocably. No longer was the cosmos a gentle ocean for humanity to sail, but a sea riddled with storms and whirlpools, each discovery deepening the sense of awe and caution. Earth orbited in a fragile sanctuary, shielded by its magnetic field, blessed by chance against solar tempests, overlooked by the worst of the galactic cataclysms. But this protection was not permanent, nor universal. Beyond the cradle stretched a landscape where danger and beauty were inseparable, where every point of light carried within it both promise and peril, the early investigations of the space age had done more than reveal new science. They had unveiled a truth that was as philosophical as it was physical. The universe was not hostile in intent, but hostile by nature. Its laws permitted life, but they did not guarantee it. To step into space was to step into an environment that cared nothing for survival. It was an awakening, a humbling recognition that exploration would never mean escape from danger. Instead, it meant walking knowingly into it, armed with knowledge, fragile technology, and the resilience of curiosity. Humanity had begun its catalogue of deadly places, and the list would only grow by the closing years of the 20th century. The universe had begun to reveal its darker truths with greater clarity. The age of orbital telescopes had arrived. Instruments like the Hubble Space Telescope and the Chandra X-ray Observatory lifted human vision above the turbulence of Earth's atmosphere, granting eyes that could see far deeper, sharper, and across wavelengths once hidden. What these machines recorded was both extraordinary and unsettling. Hubble, launched in 1990, gazed not only into the depths of time, but into the hearts of galaxies. There it found black holes, not as theoretical curiosities, but as living engines. Stars were not merely companions to black holes, they were prey. Observations revealed disks of matter swirling at near-light speeds, heated to such extremes that they glowed across the electromagnetic spectrum. These accretion disks became luminous beacons of destruction, light born from the violent shredding of stars. Sometimes, tidal forces tore a star apart completely, flinging streams of plasma into space before the remnants spiraled into oblivion. What had once been conjecture that black holes could actively devour was now painted across the cosmos with chilling precision. Chandra, with its sensitive X-ray eyes, peered deeper still. It revealed the presence of neutron stars unlike any previously imagined. Some carried magnetic fields 1,000 trillion times stronger than Earth's, so intense they twisted the very vacuum of space around them. These were magnetars, exotic remnants of stellar collapse, whose fields could strip electrons from atoms at vast distances. Their occasional flares released more energy in a fraction of a second than the sun would emit in 100,000 years. They were rare, but not impossibly so, and their existence underscored a sobering truth. The universe harbored states of matter and force that defied ordinary comprehension at the same time. Astronomers began mapping the remnants of supernova with unprecedented clarity. Hubble and Chandra together traced shockwaves racing outward at thousands of kilometers per second, sculpting delicate filaments of gas, luminous in every color of light. Yet beneath the beauty lay devastation. These expanding shells of energy carried enough force to sterilize nearby worlds, their radiation lethal across light years. The Crab Nebula, Cassiopeia A, and countless other remnants became cosmic graveyards, monuments to destruction, yet also nurseries for the elements of future worlds. It was a duality humanity was only beginning to understand: death and creation, intertwined at every scale. Gamma-ray bursts two-stepped out from the shadows of uncertainty. With the launch of satellites like Bepo-X in the 1990s, astronomers finally pinpointed their origins. They were not near. They were cosmically distant, billions of light-years away. And yet, even from such distances, their brilliance rivaled the light of entire galaxies. The implication was staggering. If such explosions could be seen across the observable universe, then their true luminosity was beyond anything previously conceived. Some bursts were linked to hypernovae stars collapsing into black holes, their energy funneled into narrow jets of relativistic matter. Others were traced to neutron star collisions, where matter so dense it defied physics itself collided and released torrents of radiation, while simultaneously forging heavy elements like gold and platinum. The brightest, deadliest explosions known were no longer mysteries. They were real, abundant, and scattered across the heavens. Yet not all discoveries glowed with fire. Some carried a quieter menace. In the 2000s, astronomers confirmed the existence of rogue planets, worlds cast adrift, expelled from their parent stars, wandering the interstellar dark, cold, lightless, and eternal in their solitude. They drifted invisibly between stars. Though not explosive, they were no less lethal. To encounter one in interstellar travel would mean collision without warning, an impact at speeds where even the hardest alloys would melt into plasma. These rogue worlds reminded humanity that danger came not only from light, but from shadow, not only from energy, but from silence. Together, these observations reshaped the cosmic narrative. The universe's deadliest places were not distant. Rarities hidden in forgotten corners. They were everywhere. Black holes anchored galaxies. Neutron stars and magnetars were scattered among the stars. Supernova and gamma-ray bursts lit the sky with violent regularity. Rogue planets outnumbered the stars themselves. The deadly universe was not the exception, it was the rule. Life, and the fragile safety of Earth, was an anomaly. For the first time in history, humanity could not look at the night sky without this awareness. Every pinpoint of light carried with it the possibility of danger, a collapsed core, a drifting world, an ancient explosion still racing across space. And yet, within this recognition lay a paradox of beauty. To know the universe in its violence was also to see it more fully, to grasp the true scale of forces that had shaped galaxies, stars, planets, and even life itself. The abyss was not empty, and the danger was not meaningless. It was the language of the cosmos, written in fire, silence, and destruction, the very conditions that made existence possible. When Hubble turned its eye toward the heart of galaxies, it uncovered not just isolated black holes, but colossal ones, millions and billions of times more massive than the Sun, dwelling at the centers of nearly every great spiral and elliptical. In the galaxy M87, Hubble traced a jet of matter, narrow and focused, blasting outward for thousands of light years, launched by a central black hole heavier than 6 billion suns. The energy was not subtle. It was ferocious, transforming the very fabric of the galaxy's core. The Event Horizon Telescope would later capture the first image of M87's black hole, a glowing ring of light bent by gravity around a shadow. It was not an artist's concept, but the first true glimpse of a place where space-time itself collapsed. Humanity, at last, had seen one of the deadliest places in existence. Chandra added detail invisible to Hubble. With its X-ray vision, it traced the scars of galactic violence, shock fronts millions of light-years across, born from black holes stirring the hot gas of galaxy clusters. These cosmic behemoths did not quietly swallow. They reshaped entire environments, carving cavities in intergalactic gas, driving storms of matter larger than entire galaxies. The serene images of the night sky, so long admired by poets and dreamers, were revealed as facades. Underneath, galaxies lived and died by the energy of their hidden cores. The neutron stars, revealed by Chandra and other telescopes, deepened the sense of unease. Magnetars, in particular, forced physics into new realms. Their surfaces boiled with magnetic energy so great it could distort atomic structure itself. On Earth, atoms align into molecules, molecules into matter. In the presence of a magnetar, atoms were stretched into spindles, pulled apart by magnetic fields that dwarfed any laboratory force. Occasionally, these stars cracked under their own stress, releasing starquakes, bursts of radiation so intense that in 2004, one flare from a magnetar 50,000 light-years away briefly altered Earth's ionosphere. To think that a dying star halfway across the galaxy could leave its fingerprint on the skies of Earth was to be reminded how little distance protected against cosmic violence. Supernova remnants, mapped in exquisite detail, offered a different perspective. Images of Cassiopeia A showed layers of gas expanding outward from a single stellar death only 350 years ago. The debris was not uniform. It was turbulent, filled with knots of heavy elements hurled into space at thousands of kilometers per second. These explosions were not simple detonations. They were sculptors of galaxies, distributing oxygen, iron, silicon, and gold into the interstellar medium. Their shockwaves compressed clouds of gas, triggering new waves of star formation in destruction. They sowed creation, but the energy released made clear the stakes. To exist near such an event was to be erased. Gamma-ray bursts continued to haunt astronomy with their staggering brilliance. In 1997, Beppo Sayx finally pinpointed one such burst to a distant galaxy, confirming that these were extragalactic events. What had once been thought rare was revealed to be common. Hundreds occurred across the universe each year. Their power was almost unbearable to comprehend. A single burst, lasting less than a minute, released as much energy as the sun would emit across its 10 billion year lifetime. Their jets, narrow but devastating, raised existential questions. If one were to ignite within a few thousand light of Earth, aimed by chance in our direction, the ozone layer would collapse. The surface would be bathed in sterilizing radiation, and life might vanish. The record of past mass extinctions on Earth even hinted that such events may have played a role in erasing species before. The night sky was no longer merely a source of awe. It was a reminder that survival itself was precarious. Amid these luminous revelations came discoveries of a quieter but equally haunting kind. Rogue planets, invisible wanderers adrift between stars, became a new frontier of danger. In 2011, data from microlensing surveys suggested they might number in the hundreds of billions within the Milky Way alone. Some estimates placed their abundance higher still, perhaps trillions of worlds cast adrift, stripped from their stars during gravitational encounters, forever drifting in darkness. These planets carried no light, no warmth, and no promise of safety. For any life upon them, survival would be unimaginable. For future travelers of the cosmos, they represented an invisible minefield, lurking in the void between stars. That the galaxy was filled with such dark wanderers underscored a grim truth. Emptiness was not safety, and the void was not empty. As the catalogue of deadly places grew, a realization spread across astronomy. These were not exceptional curiosities, confined to rare corners of the cosmos. They were abundant, woven into the very structure of galaxies. Every cluster of stars concealed black holes. Every massive star would end in a supernova or collapse into a neutron star. Every galaxy harbored eruptions of gamma-ray bursts. Every stellar system could cast out planets into exile. The universe was not sprinkled with danger. It was built from it, and yet, within this revelation, there was a deeper paradox. Life on Earth, fragile as it was, owed its existence to this same violence. Without black holes shaping galaxies, there might be no spiral arms to nurture stars like the sun. Without supernova, there would be no oxygen to breathe, no iron in blood, no calcium in bone. Without neutron star collisions, there would be no gold to glint in rivers, no platinum to forge into tools. Even rogue planets spoke of the chaotic forces that sculpted star systems, forces that also produced habitable worlds. The breakthrough observations of the late 20th century did not merely expand the list of cosmic dangers, they reshaped humanity's understanding of its place. To exist was to stand at the intersection of creation and annihilation, to live in a universe where the same events that threatened extinction also made life possible. The deadly places of space were not accidents, not aberrations, they were the very engines of the cosmos. The deeper the gaze of telescopes reached into the cosmos, the sharper the paradox became. The universe was not a serene stage of distant lights, but a theater of endless upheaval. Stars died in violence, yet from their ashes new stars were born. Galaxies tore into one another, yet their collisions seeded fresh generations of suns. Everywhere, destruction walked hand in hand with creation, as though the two were not enemies but inseparable halves of the same law. A single supernova could erase all life within dozens of light years. sterilizing worlds with radiation and shock waves. And yet, it was supernova that spread oxygen, carbon, and iron across interstellar space, the elements of breath, bone, and blood. Without their detonation, there would be no rocky planets, no blue oceans, no fragile beings to ponder their origins. The hand that struck was the same hand that gave. It was here that scientists began to glimpse a kind of cosmic ecology, a cycle in which violence was not waste, but nourishment for the next age of stars. Catastrophe was not the end, but the soil from which new beginnings emerged. Nowhere was this duality more haunting than in the magnet. These rare neutron stars, wrapped in magnetic fields trillions of times stronger than Earth's, seemed to embody chaos itself. They burst without warning, flaring with X-rays and gamma rays that could ripple across light years. The giant flare of December 2004 from the magnetar SGR 1806-20 was so powerful that for a fraction of a second it outshone the rest of the Milky Way combined. Earth, though half a galaxy away, felt its touch as the upper atmosphere shuddered under its radiation. No warning, no defense, just a brief reminder that life lived at the mercy of distant stars. And yet, the same physics that created matter also forged the heavy elements in neutron star collisions, providing the very gold that civilizations mined and treasured. Again, the pattern repeated. Devastation as midwife to abundance. Black holes, long thought to be the ultimate destroyers, revealed their own strange dual role. As matter spiraled into their depths, it unleashed energy in the form of quasars and jets enough to heat entire galaxies and regulate their growth. Without this feedback, galaxies might collapse under their own weight, their stars forming too quickly, exhausting their fuel, and dying in unison. Black holes, paradoxically, were gardeners as well as predators, pruning galaxies so they could endure for billions of years. The most feared entities in the universe were also hidden architects of cosmic order. For astronomers, this revelation posed not only scientific questions, but philosophical ones. Why was the universe arranged this way? Why was danger inseparable? From beauty, destruction from creation, it was as if the cosmos could not exist without perpetual tension, a balance in which safety was an illusion and violence a necessity. Every atom in a human hand once belonged to a star that died in agony. Every breath of air was the gift of explosions that sterilized vast swaths of space. Existence itself was built from catastrophe. This deepened the mystery. The universe was not merely violent by accident, it seemed structured to be so. Galaxies thrived on upheaval, stars recycled through collapse, and life emerged from the chaos of stellar death. In this cycle, the line between enemy and ally blurred. Danger was not a foreign invader, but the engine that made order possible. And in that unsettling truth lay a question that science could not yet answer. Was violence not only the price of existence, but its very foundation? The more scientists uncovered, the more the paradox began to resemble a law of its own, a strange symmetry woven into the fabric of the cosmos. It became clear that without violence, the universe would stagnate. Galaxies, left unchecked, would collapse into overabundance, birthing stars too quickly, leaving only short-lived giants that burned themselves out in fury. Without the disruptive hand of black holes regulating their growth, galaxies would suffocate, under their own brilliance, shining bright for a moment and then going dark forever. Violence, in this sense, was a form of balance, ensuring not only destruction but endurance across unimaginable spans of time. In the cold silence between stars, astronomers found echoes of these cycles preserved in vast remnants, shells of supernova. Spreading across light years, their filaments glowing like ghostly fingerprints of death. These remnants were not only tombs, but nurseries, where gas clouds compressed under the weight of shock waves, kindling new generations of stars. The beauty of the Crab Nebula, with its delicate threads of luminous gas, belied the ferocity of the explosion that birthed it. Within its glowing arms, the cycle of death and rebirth was inscribed, a reminder that the violence of one era became the genesis of the next. But not all discoveries could be reconciled with such symmetry. Magnetars, with their erratic flares, remained a puzzle of unease. Some theorists suspected their quakes, starquakes, splitting crusts of degenerate matter, were not just side effects, but essential, catastrophic releases of energy needed to stabilize their structure. Others proposed that such events might be clues to physics still unknown, hinting at the exotic behavior of matter crushed beyond nuclear density. The fear lay not only in their bursts but in what they implied, that the universe might hold realms of instability still unimagined, forces capable of reaching across light years to alter the fates of worlds gamma ray. Bursts, too, confounded attempts at reconciliation. These titanic beacons, pouring out more energy in seconds than the sun would in its entire lifetime, were both breathtaking and terrifying. Some originated from the collapse of massive stars into black holes, others from the merger of neutron stars. In either case, the violence was total, a kind of annihilation that eclipsed any sense of balance. If one such burst occurred within our galactic neighborhood and happened to be aligned with Earth, the fragile web of life would unravel in moments. The paradox here was starker than ever. The very events that seeded galaxies with heavy elements also carried the power to extinguish any chance of life flourishing under their watch. Creation and annihilation were inseparable, and their knife-edge balance dictated the history of everything. For many scientists, this deepening complexity was not just a scientific puzzle, but a mirror of human existence. Life itself thrived through struggle, through mutations spurred by stress and catastrophe. Even on Earth, evolution's great leaps were written in extinction events and planetary upheavals. In this way, the cosmos reflected life's own story: survival born from adversity, progress fueled by catastrophe. The violence of the universe was not foreign to life, but embedded in its very structure. To study the heavens was, in a sense, to see existence's reflection on a far grander scale. The philosophical weight of these discoveries pressed heavily. Was danger not merely an obstacle, but a requirement? If galaxies needed black holes to shape them, if stars needed to die violently to give rise to planets, if bursts of cosmic fury created the conditions for new worlds, then perhaps fragility was not a flaw in the universe, but its method. Perhaps survival itself was never meant to be safe, but a fleeting miracle carved out of chaos. And in this reflection, humanity began to confront a truth as haunting as it was humbling, that the universe was not designed for comfort, nor for destruction, but for an eternal dance between the two, from the smallest particle to the largest galaxy. The mystery deepened, not because the universe was disordered, but because it was ordered through violence. The cosmos did not merely contain deadly places, it thrived upon them. And as telescopes and satellites revealed more of these truths, humanity stood in awe, realizing that its own survival was a quiet defiance against the very forces that shaped it. At the farthest reaches of knowledge, where equations strain and instruments falter, the universe reveals a face both terrifying and sublime. It is here, at the extreme edge of science, that human understanding bends under forces too vast to grasp, where the familiar laws of nature begin to blur into something unrecognizable. The black hole event horizon is one such frontier, a threshold where time itself slows, stretching toward infinity. To an outside observer, an object falling toward the horizon appears frozen, its final moments suspended forever in a fading glow. Yet for the object itself, time continues unhindered, vanishing into the abyss in a plunge from which no light can escape. Einstein's equations predicted this paradox, but even now, with decades of evidence, the reality remains unsettling, that there are places in the cosmos where the very concept of time ceases to hold meaning. To approach such a boundary is to confront the limits of existence itself. If black holes represent the undoing of space-time, neutron stars embody the undoing of matter. These stellar remnants crush mass with such intensity that a single teaspoon of their substance weighs billions of tons, heavier than mountains. Their surfaces are sheathed in crusts of iron, beneath which matter dissolves into a fluid sea of neutrons. Perhaps even stranger states, beyond human conception, quark, matter, hyperons, or something yet unnamed. The structure of such an object defies imagination. An entire star compressed into the size of a city, its gravity so intense that escape requires 2/3 the speed of light. And in their magnetic brethren, the magnetars, this density fuses with magnetic fields so extreme. They can tear electrons from atoms across vast distances. To exist near one is not to live at all, but to dissolve into atomic debris. The violence of these objects extends outward. Tidal forces near compact stars can shred entire planets and suns, stretching them into luminous ribbons of gas that spiral toward oblivion. Astronomers have witnessed such events, stars torn apart, in dazzling streams of light as they fed the insatiable mouths of black holes. These tidal disruption events transform galaxies into theaters of horror, showing how even stars, the anchors of cosmic stability, are not immune to destruction. But the cosmos offers even greater extremes. Radiation fields unleashed in the collapse of hypermassive stars, in what scientists call hypernovas or collapses, dwarf all known explosions. These cataclysms forge black holes in their death throes, releasing beams of gamma radiation capable of sterilizing entire regions of a galaxy. The energy output in mere seconds surpasses the lifetime yield of countless stars. If such a beam were ever to sweep across Earth, life would vanish without warning, erased in silence. That such forces exist at all is a reminder of how fragile the bubble of safety truly is, and still, these discoveries may not represent the ultimate boundaries. The universe is vast, and our instruments have touched only a fraction of its secrets. There may be phenomena beyond even the most violent known explosions, processes unfolding in the hearts of galaxies, in the dark corridors of space-time, or in the hidden dimensions that physics only whispers of, just as gamma ray bursts were once invisible to us. Perhaps there are still dangers beyond detection, events waiting to be unveiled by future instruments. If the past century has revealed anything, it is that the universe holds more extremes than human imagination is yet able to conceive. The edge of science, then, is not a wall but a horizon, a shifting boundary between knowledge and the unknowable. And as humanity peers across it, the lesson is clear. The universe is not simply hostile or kind, but something greater. A vast and restless stage where creation and annihilation are bound in eternal tension. At its extremes, science does not only uncover facts, it confronts the human mind with mysteries so deep that they border on the philosophical, even the spiritual. In these deadly places, the question is not only how the cosmos works, but why. It is written this way: to approach the event horizon of a black hole is to witness reality itself torn apart. The phenomenon of spaghettification, as physicists call it with disarming simplicity, is no metaphor but a literal stretching of matter. The closer one side of a body lies to the singularity, the stronger the pull. At first, this difference is negligible, but nearer the abyss it grows with unimaginable ferocity. A human body, a spacecraft, even a planet would be drawn into a column of atoms, stretched like cosmic taffy until nothing recognizable remained. It is a violent end, yet also a profound illustration of gravity's dominion, not a passive attraction, but an active sculptor of matter, time, and space, within neutron stars. Another frontier beckons, a place where the rules of matter itself collapse. In laboratories on Earth, scientists crush atoms with particle accelerators, probing quarks and gluons, the fundamental particles bound inside protons and neutrons. But even these experiments pale before the pressures inside a neutron star's heart. Some theories suggest that within such densities, neutrons themselves dissolve, releasing their quarks into a sea of unbound particles. Others propose the birth of strange matter, an exotic substance so stable it could, in theory, convert normal matter into its own likeness on contact. If such matter truly exists, then a single droplet could, under the right conditions, consume entire worlds. The thought is speculative, but it underscores the truth. Neutron stars are not just objects of crushing weight, but laboratories of physics inaccessible anywhere else in the cosmos. And then there are the colossal deaths of stars, more massive than any the sun could ever rival. In the collapse of such titans, ordinary supernova are insufficient to describe the ferocity. Instead, per instability supernova occur, where photons within the star transform into matter and antimatter, destabilizing the star's balance until it detonates entirely, leaving nothing behind. These are explosions of annihilation, stars erased completely, their substance hurled into space in a single devastating instant. More violent still are collapses, where a massive star's core collapses directly into a black hole, unleashing twin jets of energy that roar outward at near light speed. The gamma ray bursts born in such events are the brightest lighthouses in the universe, but also its deadliest. For a planet caught within their beam, survival is impossible. Yet these are only the phenomena we know. The possibility of quark stars, objects denser than neutron stars, but not yet black holes, lingers on the edge of theory. The whispers of fast radio bursts, sudden millisecond flashes of radio energy, hint at magnetar flares, or perhaps stranger processes altogether. The dark matter and dark energy that shape the vast majority of the universe remain inscrutable. Who can say whether their influence harbors dangers unimagined, tides of invisible force that could, under the right conditions, unravel the structures of galaxies? The cosmos has revealed so many surprises already that caution compels humility. To claim we have catalogued every danger would be hubris of the highest order. Even the spaces between stars are not safe. The radiation that floods intergalactic voids, the relics of quasars and supernova, bathes galaxies in unseen light. High-energy, cosmic rays, protons accelerated to speeds nearly indistinguishable from light, strike Earth daily there. origins stretching back to ancient cataclysms. They are rare in individual cases, yet relentless in their persistence. They remind humanity that no place, not even a small planet cocooned in its atmosphere, is ever fully shielded from the universe. Beyond and in the farthest reaches of thought, cosmologists speculate on catastrophes not tied to stars at all, but to the universe itself. The slow decay of the vacuum, the possibility that our cosmos rests in a false minimum of energy, suggests a fate where reality could one day collapse into a more stable state. If such an event occurred, it would sweep across space at the speed of light, erasing the laws of physics as we know them. There would be no warning, no survival, only the cold transformation of existence itself. It is an idea born from equations rather than observation, but it speaks to the true edge of science, where knowledge merges with fear, and where the mysteries of the cosmos are inseparable from the fragility of life within it. The extreme edge of science is thus not merely a catalogue of deadly places, but a meditation on what it means to exist in such a universe. For every horror lies a hidden necessity, and for every danger, a mystery that draws human curiosity further. Black holes teach of gravity's secrets, neutron stars of matter's ultimate form, supernova of the cycles that sustain galaxies. Even the most violent events are teachers, demanding reverence for their destructive power and gratitude for the unlikely sanctuary Earth provides. And yet, as instruments sharpen and theories evolve, the horizon of fear continues to expand. Each revelation brings awe, but also unease. For in studying the cosmos, humanity discovers not only the grandeur of existence, but the precariousness of its own survival. The edge of science is not just where knowledge ends, it is where humility begins. The universe, in all its grandeur, is not a place of quiet stability. It is a stage where destruction is not an accident, but a principle, where cataclysm is written into the laws of physics. The leading theories of modern astrophysics do not shy away from this truth. They embrace it, revealing how every structure of order is born from cycles of collapse and fire. Black holes stand as the most profound expression of this idea. According to Einstein's general relativity, when a massive star exhausts its nuclear fuel, gravity overcomes every force that once resisted it. No pressure, not even the quantum strength of degenerate matter, can withstand the inward pull. The result is collapse without limit, a singularity where density reaches infinity and space-time itself folds inward. Around this hidden abyss forms the event horizon, a one-way boundary where even light cannot escape. And surrounding that, an accretion disk often flares into brilliance, a maelstrom of matter heated to billions of degrees as it spirals inward, releasing energy so fierce it can outshine an entire galaxy. These are not silent voids. They are furnaces of annihilation, shaping galaxies through jets and winds, seeding interstellar space with turbulence and heat. Stellar evolution provides the blueprint for these outcomes. Stars are not eternal lamps, but engines with lifespans carved into their cores. Low-mass stars, like the Sun, end in quiet deaths, shedding their outer layers to form planetary nebulae and leaving behind white dwarfs. But for massive stars, the path is violent. They live fast, burning their fuel in millions of years rather than billions, building heavier elements in their cores until iron forms, the element that cannot yield energy through fusion. When fusion halts, the star collapses inward in a fraction of a second. The rebound shock, powered by neutrinos and imploding shells of matter, explodes outward as a supernova, scattering carbon, oxygen, and iron into the galaxy. From these ashes, new stars and planets form. Death becomes Genesis. Among the survivors of such violent deaths are neutron stars, remnants no larger than a city, yet more massive than the Sun. Their matter is crushed into densities of 1 billion tons per teaspoon. Their surfaces swept by magnetic fields trillions of times stronger than Earth's. Some neutron stars spin hundreds of times per second, their radio beams sweeping across space like cosmic lighthouses. Others, the magnet, erupt without warning, releasing bursts of gamma rays and X-rays, so powerful they momentarily outshine every other source in their galaxy. In December 2004, such a flare from the magnetar SGR 1806-20 released more energy in 1/10 of a second than the Sun emits in 150,000 years. If it had been closer, it could have scorched the biosphere of Earth itself. These are not abstract theories. They are recorded events, measured by satellites and seared into the memory of science. Gamma bursts remain among the most violent expressions of stellar death. Models suggest 2 primary origins. The first, hypernovae, where massive stars collapse into black holes, driving twin jets of matter and radiation at nearly the speed of light. The second, mergers of compact objects, when neutron stars spiral together and collide, releasing both gamma rays and the ripples of space-time known as gravitational waves. In 2017, such an event was observed, GW170817. Its light captured across the spectrum, its gravitational signature detected by LIGO and Virgo. It confirmed that the collisions of neutron stars forge heavy elements, including gold and platinum, spreading them into the galaxy like embers of creation. Violence, once again, proved to be the architect of beauty. On larger scales, galaxies themselves live and die through destruction. Their elegant spirals and elliptical shapes are not fixed, but sculpted by collisions and mergers. The Milky Way is no exception. In 4 billion years it will merge with the Andromeda Galaxy, their stars flung into new orbits, their black holes spiraling together in a final titanic union. What may appear as chaos is, in truth, the natural rhythm of cosmic architecture. Starburst galaxies, glowing with furious creation, are often powered by the shock waves of such encounters. Destruction feeds birth, and disorder builds the structures that later inspire human wonder. Through all these models, the consensus emerges with clarity. Danger is not a flaw of the cosmos, but its foundation. From the nuclear physics in stellar cores to the gravitational dynamics of galaxies, destruction is not an intruder. It is the very process by which the universe evolves. Stars die so that planets may form. Black holes consume, yet regulate galaxies. Magnetars erupt, yet reveal the depths of matter's resilience. Gamma ray bursts obliterate, yet scatter the seeds of chemistry across interstellar space. Mainstream science does not romanticize these forces. It describes them with equations, models, and simulations, supported by the weight of observation. But behind the data lies a profound truth, that the universe thrives not in spite of violence, but because of it. Creation and destruction are not opposites. They are 2 faces of the same eternal cycle, woven together in the fabric of cosmic time. The most striking feature of these mainstream theories is not their speculation, but their precision. Each destructive engine has been traced not only in thought, but in light, in data, in the language of observation that links mathematics to reality. The physics of accretion disks, for instance, is no longer a realm of imagination but of direct evidence. Telescopes like Chandra and new STR have revealed X-rays pouring from the disks around black holes. Each photon a clue to the nature of matter spiraling toward oblivion. Models of viscosity and turbulence built upon the mathematics of magnetohydrodynamics describe how plasma, threaded with magnetic fields, spirals inward with growing fury. In the final orbits before crossing the horizon, matter moves at half the speed of light. Its energy released as radiation that can dominate the brightness of an entire galaxy. These active galactic nuclei, once mistaken for stars, are now recognized as black holes feasting, their violence so luminous that they can be seen across the cosmos. The physics of jets remains one of the most astonishing demonstrations of order emerging from chaos. As matter swirls in magnetic fields, twist into colossal structures, funneling plasma into narrow beams that pierce the intergalactic dark. These jets extend for millions of light years, carrying energy far beyond the confines of the host galaxy. They regulate the growth of galaxies by heating interstellar gas, preventing it from cooling into stars too quickly. In this way, the violence of accretion sustains cosmic balance. Without destruction, there would be no structure, only disorder. Of another kind, at the smaller scale of stars, the life cycle remains the most vivid testimony of the universe's duality. Every atom of oxygen in human lungs, every molecule of calcium in bones, every trace of iron in blood was born in the death throes of stars. The periodic table itself is a cosmic record of destruction. Hydrogen and helium came from the Big Bang, but carbon, nitrogen, silicon, and iron came from supernova. Even heavier elements, uranium, thorium, gold, were forged in the titanic collisions of neutron stars. Observations of GW 170817 proved this beyond theory. When two neutron stars merged in that distant galaxy, not only did they send gravitational waves across the universe, but their light revealed the birth of heavy elements in quantities unimaginable. In that instant, the violent crash of dead stars wrote the chemical chapters of future worlds. Mainstream astrophysics also addresses the strange, almost paradoxical role of with magnetic fields strong enough to warp the quantum vacuum. They present a laboratory of extremes far beyond earthly experiment. Their sudden flares remain imperfectly understood, perhaps the cracking of their crusts under magnetic tension, perhaps reconnection of field lines unleashing bursts of energy. Whatever the mechanism, the outbursts remind scientists that even after collapse, even after matter is crushed into unimaginable density, stars do not rest in peace. They twitch, they rupture, they scream into the void with energy bursts that challenge the imagination at cosmic scales. The violence of galactic dynamics is no less profound. Computer simulations, based on the laws of gravity and dark matter, reveal that galaxies are not solitary islands, but restless travelers, colliding and merging through the ages. Hubble and other observatories have imaged galaxies their spirals shredded, their stars cast adrift, their black holes drawing nearer in a slow, inevitable dance. These mergers ignite starbursts, flood interstellar space with radiation, and reshape the cosmic web itself. What appears destructive from afar is, in truth, the means by which structure emerges from chaos, the way galaxies evolve into new forms. The agreement among scientists is striking. Across disciplines, from stellar astrophysics to galaxy evolution, from particle physics to cosmology, the evidence converges on a single theme. Destruction is not an anomaly, but a necessity. Without supernova, the universe would lack the elements for life. Without black holes and their feedback, galaxies would collapse into uncontrolled star formation. Without gamma-ray bursts and the dispersal of heavy elements, planets like Earth could never form. Violence is not only frequent, it is foundational. Yet even in this consensus, mystery remains. Singularities themselves are beyond the reach of present theory. General relativity predicts their existence, but at their core lies the failure of physics as it is known. Matter crushed to infinite density, space-time folded into nothingness. These are signals that the current framework is incomplete. A true quantum theory of gravity, uniting relativity with quantum mechanics, may someday reveal what happens in those ultimate depths. Until then, black holes remain the most extreme test of human understanding. Places where equations fracture and imagination falters. The mainstream view is therefore a blend of certainty and humility. It confirms that destruction is inseparable from creation, that cosmic violence is a necessary scaffold for order, but it also acknowledges its own limits, where even the most advanced models cannot yet penetrate. This is perhaps the most human feature of science, to recognize that the universe, though revealed in fragments, remains larger, deeper, and stranger than any complete story we can yet tell. At the edge of human imagination, science stretches into speculation, where equations hint at possibilities stranger than myth. If the mainstream view of the cosmos paints destruction as necessary for creation, the speculative edge dares to ask whether there exist forces so alien, so absolute, that they lie beyond the reach of survival. These are the visions that shimmer between mathematics and mystery, theories unproven yet grounded in the whispers of physics. Here the universe reveals not only what is known, but what may lurk unseen, waiting, patient and eternal. Among these possibilities is the concept of quark, stars hypothetical corpses of stars, denser even than neutron stars. In a neutron star, gravity presses matter until protons and electrons collapse into neutrons, yielding an object 1 billion tons heavy per teaspoon. But some theorists suggest that under even greater pressure, neutrons themselves may dissolve into a sea of quarks, the fundamental particles that form the building blocks of matter. Such an object, smaller yet more compact than any neutron star, would radiate differently, perhaps emitting bursts of light and energy beyond known extremes. If quark stars exist, they may already lie hidden among the pulsars astronomers observe, masquerading as familiar objects while harboring stranger truths. Their existence would reshape our understanding of matter itself, revealing that even the so-called end states of stars are not truly final. Equally haunting is the idea of primordial black holes, relics of the infant universe. Unlike stellar black holes, born of collapse, these would have formed in the turbulence of the Big Bang itself, when quantum fluctuations could have condensed into objects of immense density. They may range in size from mountains to atoms, from supermassive anchors of galaxies to invisible specks drifting through interstellar space. If such objects exist, they could account for the elusive dark matter, unseen yet influencing galaxies with their gravity. More chilling still is the possibility of one such primordial black hole wandering unseen into our solar system, its presence betrayed only by the subtle tug on planetary orbits, a cosmic assassin hiding in plain sight. Speculation grows darker when physics confronts the stability of the vacuum itself. According to some interpretations of quantum field theory, the vacuum of space, The very fabric of existence may not be truly stable, but only metastable. If so, a more stable state could, in theory, emerge spontaneously, expanding outward at the speed of light. This event, known as vacuum decay, would annihilate the universe instantly, erasing all structure, all matter, all law of physics, with no warning and no resistance. It is not a matter of hostility, but of inevitability, should the parameters of the cosmos permit it. To contemplate this possibility is to confront the most existential of questions, that the universe, for all its grandeur, may be balanced on a knife's edge. Its existence a fleeting accident in an ocean of potential realities. Yet speculation does not only conjure destruction, but also the allure of passage. Wormholes, predicted by solutions to Einstein's equations, remain both tantalizing and treacherous. They are envisioned as tunnels through space-time, bridges linking distant corners of the cosmos. If real, they could offer escape, perhaps even a means to outrun cosmic catastrophe. But equally, they could be traps, unstable, collapsing in bursts of radiation, or opening into places hostile beyond comprehension. The mathematics suggests that to remain open, such structures would require exotic matter with negative energy, a substance never observed, still in the tension between possibility and impossibility. Wormholes linger as a symbol of cosmic duality, salvation and annihilation intertwined. Beyond even wormholes lies the question of parallel universes. If the multiverse exists, then our cosmos is but one bubble in an endless foam. Could forces from beyond bleed into our reality? Could black holes be gateways not only to collapse, but to other domains? These ideas remain untested, unprovable. For now, yet they compel thought. For if universes can collide or overlap, the dangers we perceive may be but shadows of greater storms beyond our comprehension. In the speculative frontier, science becomes philosophy in motion. It dares to ask, not only what is, but what might be, and whether the most dangerous forces are not those we can see, but those we cannot yet imagine. The ultimate doomsday question lingers like a silent pulse. Is there a phenomenon capable of ending everything instantly? Not only stars and galaxies, but the universe itself. Perhaps the universe has already witnessed such endings countless times, in realities parallel to ours, invisible but real. Perhaps our own survival is not due to cosmic kindness, but to the improbable luck of existing in a bubble, where danger has not yet struck. And in that thought lies the deepest reflection. The universe may not simply be violent, it may be precarious. Its beauty, its order, its ability to create life, may all be temporary expressions balanced upon unfathomable forces. To exist within such fragility is both terrifying and wondrous, for it means that against the backdrop of annihilation, every breath, every star, every world is a fleeting miracle, born not in safety, but in the shadow of cosmic uncertainty. Some physicists suggest that the most formidable force may not be hidden in matter at all, but in the very expansion of the universe. Dark energy, the mysterious driver accelerating cosmic growth, remains one of the most profound puzzles of modern science. If its strength were to change over time, the consequences could be catastrophic. One speculative vision, known as the Big Rip, imagines a future where dark energy grows ever stronger, pulling galaxies apart, then stars, then planets, and finally the very atoms themselves. In such a scenario, the universe would not end in fire or collapse, but in an unraveling, a slow, merciless stretching until no structure remains. It is destruction at its most elegant and merciless, written not in explosions but in silence. Some models predict such an end could occur tens of billions of years from now. Others leave the timeline indefinite. What matters is the principle that the very fabric of space, the canvas on which all else is painted, could turn against its own creations. Alongside this vision lies another, the possibility that the universe is not a one-time event, but part of a cycle of death and rebirth. Theories of a big bounce suggest that our cosmos may one day collapse, not into nothingness, but into a state so dense that a new explosion is inevitable. In such a view, destruction is not final but transitional, each universe giving birth to another in an infinite chain. Yet for any observer within a given universe, the collapse would still mean the end of all familiar things. Whether rebirth follows does not lessen the terror of annihilation. To imagine the cosmos as a cycle is to replace finality with repetition, but it still leaves open the same question: how fragile, how impermanent is the moment we inhabit? Other speculative ideas speak of structures woven into space-time itself. Cosmic strings, hypothetical defects in the fabric of the universe, left over from the earliest moments after the Big Bang, may stretch across galaxies like invisible scars. If they exist, they could channel immense energy, their gravitational fields warping light and matter alike. Collisions between them might release bursts of power rivaling entire galaxies. No confirmed evidence has been found, but the search continues. For such relics would hold not only destructive potential, but also the key to understanding the universe's earliest seconds. Their danger lies not in their intent, but in their indifference. Scars of creation, still capable of shaping destruction. At this fringe of knowledge, speculation shades into philosophy. If vacuum decay is possible, if dark energy can rip space-time apart, if strings or other hidden structures weave through reality, then the universe may be more fragile than the human mind can bear. And yet, paradoxically, it is within this fragility that life arises. Against the backdrop of annihilation, existence itself becomes extraordinary. The fact that stars can form, that planets can orbit, that consciousness can arise to ask these questions, is an act of defiance against chaos. For scientists, these speculative theories serve not as predictions but as reminders. They remind us that the universe is not fully mapped, that the dangers we know may be only the surface of deeper truths. They remind us that the boundary between science and imagination is not a wall but a frontier, where mathematics becomes myth, and myth, in turn, may someday become observation. The edge of knowledge is both terrifying and beautiful, a mirror showing not only the cosmos, but the human desire to seek meaning within it. And so the speculative and the fringe, far from being dismissed, are embraced as possibilities, as thought experiments, testing the limits of reason. They are the universe whispering that what is known is not all that is, and that beyond the horizon may lie dangers, wonders, and truths beyond comprehension. For now, humanity looks upward with instruments and equations, knowing that certainty is impossible, but still compelled to ask, in a cosmos that creates through destruction, what forces might still wait unseen, shaping futures not yet imagined. In the 21st century, humanity stands at a new threshold. The universe, once perceived as a distant canvas, now speaks in multiple voices. Multi-messenger astronomy has transformed the way we perceive cosmic violence, combining light, neutrinos, and gravitational waves to construct a more complete symphony of the cosmos. No longer do we observe the universe solely through photons. We listen to the vibrations of space-time itself, feel the ghostly passage of particles that scarcely interact with matter, and interpret the full orchestra of energetic messengers that reach our instruments on Earth. Each detection tells a story not only of creation but of destruction, of cataclysmic events that shape galaxies and the very conditions for life. The LIGO and Virgo observatories have opened this new auditory window by capturing the faint ripples of gravitational waves. They have recorded the collisions of black holes, distant mergers of neutron stars, and the cataclysmic dance of matter in The event GW170817 marked a watershed for the first time. A neutron star collision was observed in both gravitational waves and light, revealing the birth of heavy elements and the violent forging of gold and platinum across the galaxy. Each observation is a lesson in the raw forces that sculpt the cosmos, a confirmation that the deadliest places are not rare curiosities but integral to the universe's evolution. Through these efforts, science turns the invisible into the known, charting dangers that were previously only theoretical. Meanwhile, traditional observatories remain essential. NASA's Hubble, Chandra, and Swift telescopes, alongside EOS, XMM Newton, and upcoming giants like the James Webb Space Telescope, scour the heavens for energetic explosions, rogue black holes, and stellar corpses. Each mission extends our map of the cosmos' lethal corners, revealing where gamma-ray bursts might sweep across unsuspecting planets, where magnetars flare in unpredictable fury, and where supernova shockwaves race across interstellar space. These instruments are the eyes of humanity in the dark, illuminating regions where destruction is inevitable and giving context to the fragile existence of planets like our own, closer to home, space weather monitoring has become a vital frontier. Solar flares, coronal mass ejections, and bursts of energetic particles are no longer abstract phenomena. They are immediate threats to astronauts, satellites, and critical infrastructure. Understanding these dangers requires a blend of physics, real-time observation, and predictive modeling. Each protective measure is a reminder that even the nearest stars harbor lethal power, and that survival beyond Earth demands foresight as much as courage. Exploration of habitable worlds also intersects with the study of danger. As astronomers hunt exoplanets within the so-called Goldilocks zones, they simultaneously measure radiation environments, stellar activity, and planetary magnetic fields. Worlds bathed in deadly X-rays or unshielded from frequent gamma-ray bursts are marked as perilous, even if their temperatures and atmospheres are otherwise conducive to life. The search for life, paradoxically, sharpens our understanding of death, highlighting how delicate the balance must be for a planet to sustain life amid universal violence. The collective endeavor is a slow, deliberate mapping of danger. Humanity now charts the cosmos not only to understand where life could arise, but to recognize where it would be swiftly extinguished. Through gravitational waves, neutrinos, X, and careful modeling, we are assembling a catalogue of peril, a guide to the deadliest corners of the universe. Each discovery is both a warning and a revelation, reminding us that the universe is at once wondrous and unforgiving, beautiful and lethal. As instruments grow ever more sensitive, as observatories reach farther and theoretical models refine, the boundaries of known danger expand. We are learning with every observation that to venture deeper into space is to confront forces both magnificent and deadly, and that survival requires both knowledge and reverence for the cosmos' most extreme realms. Ultimately, these scientific efforts are more than data collection. They are acts of preparation, meditation, and understanding. Humanity maps the dangers not to conquer them, but to coexist with the universe's inherent peril. In doing so, we glimpse a truth as philosophical as it is empirical. The universe does not yield its secrets willingly, and only by observing, predicting, and respecting its power can we hope to navigate its deadliest places with curiosity, courage, and humility. The universe is a theater of extremes, vast and indifferent, yet it is within this indifferent expanse that life has found a way to flourish. Humanity, a small and fragile presence on a solitary planet, peers outward into a cosmos shaped by forces that could erase entire worlds in moments. Black holes devour light and matter with inexorable hunger. Gamma ray bursts sweep across galaxies with unimaginable energy. Magnetars flare unpredictably, their magnetic fields capable of warping reality itself. Yet, amidst this deadly ballet, stars ignite, planets form, and life emerges, delicate yet resilient, in the narrow niches carved between catastrophe and creation. The paradox is stark. The same universe that harbors annihilation also nurtures the conditions for consciousness to arise, to ponder its own existence, and to dream of venturing beyond its birthplace. Knowledge of these dangers carries a weight that is both practical and philosophical. To observe a supernova's death throes, to measure the ripples of a distant black hole collision, is to confront the raw power of nature on a scale incomprehensible to the human mind. Yet this knowledge does not breed despair. It cultivates awe and humility. Understanding the lethal landscapes of the cosmos is not merely an academic exercise, but an ethical engagement with the fragility of life. Humanity's curiosity compels exploration, even knowing that beyond the protective cradle of Earth lies radiation, vacuum, and energies capable of instantaneous destruction. Each mission to the moon, each probe sent past the orbit of Neptune, each telescope scanning distant galaxies is an act of courage. Against the shadow of annihilation, a testament to the human spirit's desire to seek meaning in a universe that is neither safe nor forgiving. The reflection on mortality is unavoidable. In witnessing the death of stars and the ceaseless churn of cosmic forces, humans are reminded of their own the lifespan of a civilization, the longevity of a planet, even the persistence of the species itself, are finite threads within a tapestry woven from forces billions of years old. Yet there is a profound beauty in this awareness. The of life, mirrored by the impermanence of cosmic structures, grants significance to each fleeting moment of existence. Awareness of danger sharpens the perception of wonder. Recognition of mortality deepens the experience of life. The dream of interstellar travel is inseparable from this contemplation. Humanity imagines reaching the stars, planting life beyond Earth, yet the deadly realities of cosmic radiation, relativistic hazards, and extreme gravitational phenomena temper that ambition with caution. Exploration is not naive. It is deliberate, measured, informed by an understanding of the universe's lethal character. To voyage beyond the solar system is to step knowingly into peril, to navigate frontiers where survival depends as much on knowledge as on technology. It is a pursuit that demands respect for the cosmos, indifferent forces, and acknowledgement of the precariousness of life. Perhaps, in the end, survival is not found in fleeing from danger, but in understanding it. In embracing the knowledge that life arises and thrives precisely within the crucible of cosmic forces. The universe, in its violent grandeur, is both adversary and midwife, annihilator and creator. Human beings, in contemplating these extremes, are not powerless. They are witnesses and participants in a story that stretches across time and space. A story where peril and beauty are inseparable, and where the act of understanding the deadliest places in the cosmos is itself a form of flourishing. To exist within such a reality is to recognize that life is a fleeting miracle, blooming in the shadow of forces far greater than any single mind, yet granting a moment of consciousness to ponder, to explore, and to marvel. And so, the cosmos remains a mirror, reflecting not only the violence that surrounds us, but the resilience, curiosity, and awe that define the human experience. In this reflection, life finds its meaning not in immunity to danger, but in the courage to exist, to know, and to journey onward through a universe that is as magnificent as it is lethal.